Before we go into all the tricky examples, we're going to start off with the basics of electric field. You have learned about forces, you learn about fields either in the previous video or the last chapter from AS, if you learned it in AS. So let's start off nice and easy. We have learned gravitational fields, we have learned electric fields. How can we compare both of them? This is a past year ON12 P43 question 3. So, what's a gravitational field? Line of force. This is kind of an interesting idea. Line of force. Huh? What does that mean? So you remember when you have those planets, or let's say a parallel uniform field, something like this, when they draw these dotted lines, that's the electric field. But where will the force act on? Well, if it's a gravitational field, if it's pointing down, means if you have a mass there, it will experience a force downwards. So that's your line of force, oh? The electric field is your line of force. But hang on a second. If it is a curved planet, and I don't know, your fields are a bit like this. Actually, harder to draw. Okay, I draw another one. Let's say for some reason you have curved field lines like this. Wow, then how to draw the line of force? And then you must say like, oh, if the mass or something is here, is tangent, no? Tangent to the field line. So you don't have to write the word tangent, but just FYI, in electric fields, you can have that thing. So what is this thing? This is, I guess you could mention, it's a tangent to the line. And that gives the direction of force acting on that object. Now the nicer way to say this is actually to say a test mass lah. Why test mass? Because then you know what exactly is the quantity that this force is acting on. It acts on a mass. So mass would be an important thing in gravitational field. So you say an object, yes lah, but we want to level up a bit for A2. So let's say test mass. This is just one mark, so an independent mark if you describe it this way. For electric field, what is the line of force? Similar, but now the direction depends on the charge. If you think about this way, let's say this is the electric field. Oh, did I say E for that one? Ah, yeah. Okay, G, this one is G field. So if an electric field, only a positive charge would follow the direction of electric field. If it's a negative charge, then it will go against the electric field line. So this is a force on a negative charge, because electrons, negative charge are rebels. So it really depends on the charge. So you need to be able to describe that, but otherwise it's the same thing. Tangent to the line or the line is the direction of electric force. Now what do you say acting on the charge? Yeah, but you must specify, is it a negative charge or positive charge? So here we define direction of electric field is where a positive charge will go. Hence, we define it so we don't confuse ourselves too much. Acting on a, so you must say a positive. Positive is an important word. Positive test charge. Okay, so that's the differences between both. Almost the same, except that electric field, you can either follow the field or go against the field depending on your charge. This one got 2 marks Yeah lor. One comes from the idea where you talk about direction of electric force. Okay, blah, blah, blah. But you mentioned, positive test charge. That's an important one. So that will give you the final mark to get. Okay, moving on to B. A charged metal sphere is isolated in space. Okay. One similarity and one difference between the G force and the E force around the sphere. Similarity and differences. It's good if you have a table that summarizes the similarities and differences, so comparing the different fields. But if you imagine you have a sphere and you draw field lines, right? So I guess you could draw something like this. All the fields are pointing to the middle. For gravitational field, okay, so just give me a second. So if you have a mass m, all the fields are always pointing in the middle. That is one thing which is important to know. But for electric field, maybe it's pointing inside. Maybe it's not, maybe it's pointing out. So there's a difference there. But let's start off with the similarities first. If you look at both diagrams, I got a mass there, or maybe I have a positive charge. Look at the pattern of their fields. It is always what we call radial. Radial means like radius. How do you draw a radius of a circle? You just draw a circle like this. Radius, point out. So all is radiating out from the middle. So that's what we call a similarity between both. Both are radial fields. If you want to add more detail, you will get more marks, but I mean, you will cover more points in the mark scheme, but you only get a mark for that. But both are radial fields. Another thing you can notice about the diagram that I just draw is that the field lines are always perpendicular to the surface. See, I draw for the red color one. For the blue color one, also all the electric field or gravitational field lines must be perpendicular to the surface that they're coming out of or going into. So both are radial fields perpendicular to the surface. Sometimes people say normal because normal is also perpendicular. Perpendicular to the surface. Okay, what other things are similarities? Let's just list all since we're here. Another thing is the relationship between the variables. If we remember gravitational force, F equals to gmm over r square. Okay, what about electric field? F equals to kqq over r square. The pattern is similar. Force is inversely proportional to separation distance. F is also inversely proportional to separation distance. Did they copy each other? I'm pretty sure they did, because the pattern is literally the same. So that is another possible similarity where you can say that the force is proportional to 1 over separation distance between the two objects. Separation distance. So this can be electric force or gravitational force. You still have the same relationship. Okay, so I guess the other things you can talk about is the field lines. Field is stronger nearer to the mass, but I think this is more than enough already lah. Here I think got at least 3 marks, but we only get 1 mark for this, so any one of these would get you a mark. You can check out the mark scheme to see for more ideas of similarities and differences. Now differences. Okay, same pattern, everything same, but what is different? Nah, just now we say already ma. The force depends on the charge. Sometimes it follows E field, sometimes it doesn't. So how do we write that out? The first thing we can maybe say is that the direction of the gravitational force is always towards the sphere. So if I have an object here, a tiny mass, it will always point towards the sphere, like this. But if I have a particle here in the electric field, it really depends. If it's positive, it will go away. If it's negative, it will go towards. Can be attraction, can be repulsion, it depends. So that is the main difference between these two. So you can say G-force is always towards the sphere. This is what we call an attractive charge. They always attract each other. Two masses always attract. Let's put here attractive. But the main difference, electric force. It depends. Depends on what? The charge. So the charge. And if it's positive or negative, depending, it can be attractive or repulsive. Wow, very detailed this one. This one, there's many ways you can get your 3 marks. One of the ways is your 2 marks, because 1 mark is already up there, the top. So 1 mark is you talk about what is gravitational force and what is the electric force, the differences. Okay, this one is like this, the other one is like that. Difference. Okay, so make a table of all these things. And check out the mark scheme too for more ideas of similarity and differences. Moving on. This one look very familiar. We have seen this kind of thing before. Uniform field. Very nice. Okay, time to refresh a bit because this is important when you level up later. 2 horizontal metal plates separated by a distance. This is what we call our separation distance. A potential difference of 270 volts. Wow, very high. Maintained between the plates. Proton is between the plate. So our friend here, proton, is a positive charged particle. Explain why the gravitational field is not taken into consideration. If you remember, you have done questions from AS before, chapter 17. We say like, if proton, no need to consider gravitational field. Why leh? Now you actually have to explain it for 4 marks. Okay, let's review this a little bit. When you have this field here, these 2 parallel plates, what's the field between them? It's going to be what we call a uniform electric field. Uniform E field. Not radial. Radial is the sphere one. Now it's uniform because parallel plate ma. And that, how do we know which direction it's pointing to? The hint lies in the potential difference between the plate. The top one is what? 0 volt ma. Bottom one is what? 270 wo. So that means here is a high potential. Potential, I'm just going to shortcut and say V. V is potential ma. and this is a low potential. So that means all the electric field lines will point from high to low potential. So like this. Like this. It's kind of like saying there's positive charge here lah, pointing to negative charge. But now, no need lah, 0 volt. Okay, so this is the potential. Where will be the weight acting on the proton? Downwards, mg, very small. Where will be the electric force acting on the particle? If this is positive, it's going to go to low potential. So this is the electric force. If you feel confused, just remember, kind of think about it this way. High potential is the positive, low potential is the negative plate. Negative charge plate, so-called, but you need to start thinking in potentials already. So, how to consider? Usually we say gravitational force is very small, so we don't care. But it's 4 marks. You only get 1 mark if you say that. So we need to show evidence. Okay? Explain quantitatively. Quantitatively means, can you show evidence? Can you show your working, your calculation to prove your point? That's why it's 4 marks. So let's do this. You see Fe, you see mg. Let's calculate both of these forces separately. Let's start out with mg first lah. So the gravitational force can be calculated with mg. Do you remember how to do this? What's the mass of a proton? You can look up the front page of every exam booklet. They will show you the mass of the proton, mp. So mp should be 1.67 times, very light one, 1.67 times 10 to... Ayo, so small, got gravitational force meh? No, that's why we're supposed to prove our point by calculating this. G is 9.81, we'll get a very small number, 1.64 times 10, negative 26 Newton. So tiny. How to... Okay, never mind. Small indeed. Okay, we found our Fg. What about electric force? Let's do it on the right side here. So electric force, how to calculate? A lot of us may get brain hang. We say, oh miss, we know KQQ over R square. But there's only one charge here. How are you going to calculate? You need 2 charges for this equation to work. Don't panic. This is usually for point charges, when there's 2 point charges there. What we have here is a uniform field, my friend. So you can use all the previous knowledge that you know about uniform fields to calculate this. So for uniform fields, the electric force acting depends on the charge times the electric field strength. And this is for uniform fields only. Okay, the KQQ over R, that one, you don't have 2 point charges. It's very hard to use that one. Okay, I mean, you can derive that one for here lah, but no, this, just no. Okay, what's the charge of a proton? Plus 1 E. E is a constant. Also, you can flip to the front of your experiment. But what is big E? Electric field strength, they go give us meh? No more. We need to find ourselves. So, here's where you need to remember the second thing. Electric field strength is V over D. What is V? V is actually the potential difference from the top plate to the bottom plate. What's the difference in potential? And separation distance, I guess I should also put delta D lah. How far apart are these two? How far away are these 2 plates? So we need to find V over delta D. I'm running out of space, so I'm going to scoot over here. So E will be positive 1.6 times 10 negative 19 coulombs. That's a charge of one unit of charge. What's the delta V? We just now said there's low potential to high potential. So we're going from 0 volts on one end, right here, to 270 positive volts. So this one will be 270 minus 0 lah. No need to write 0 lah, just 270 can already. So that's your change in potential from 0 volts to 70 volts. Okay, then what else we have to divide? Distance. Okay, separation distance, we know that it's given to us 1.8 times 10 negative 2 to convert it to meters. And you get a much bigger force than gravitational force, 2.4 times 10 to the negative 15 Newton. Yay! Okay, now we have numbers we can compare. You look on the left side, you look at the gravitational force, how small is it? You look on the right side, you look at the electric force, it's much bigger, huh? So you need to summarize that in a statement down here to get your final mark. So here, you can say, they ask you explain, right? Means they're asking you why. So you can say because the electric force is much greater than gravitational force. So I kind of shortcut here and write G force, but much greater is an important idea lah. See, how many magnitudes greater? Times 10 to the negative 26 on the top left, then times 10 to the negative 15 above me. Wow, okay lah. So if you want to write it out in symbolic form, I recommend you write a sentence lah, but this is how it will look like symbolic. Fe is much bigger than Fg, hence Fg is kind of negligible. So usually when we do particles in electric fields, we don't consider the gravitational force of them because it's too small. Proton only, electron only. But if it is a charged heavy metal sphere, well, then that one floating in the electric field, there will be gravitational force lah. So questions that involve oil drop in the electric field, the oil drop will have a weight that will pull them down, so it's not so negligible anymore. But anytime you are confused and not sure whether to include or not, just calculate lah. Do these two here. Okay, 4 marks for this beautiful process of just explaining evidence. First mark is if you calculated your gravitational force. Second mark, if you knew the equations and plug in the correct values for electric force and you got a value. So how many? 1, 2, 3. Then you write the concluding statement. Must write concluding statement. Don't just show values. Must compare values. So compare. Yeah, it's behind my head. I write here, reminder lah. Whenever they ask you to suggest, explain, if you can, compare values. What am I writing? Anyway, you get the idea. So that is this first part on how to think about uniform electric fields. Now let's move on to the next one where we will zoom in a little bit more on this idea of E equals to V over D. Where did that come from and how do we apply and get ready for point charges where the field is radial? So the next one we're going to look at is ON14 P41. This is page 26. Okay. Define electric potential at a point. Wow. Have we learned this yet? Kind of, not really. We have learned it in the past in AS, but it's going to be upgraded in the next upcoming videos where we learn more exactly what is electric potential. But FYI, electric potential we know as volts. You know, 12 volt battery, 14 volt battery. V is potential. And you have potential difference, PD. Same thing, but now is at a point. So we're going to think about in terms of electric fields. So the first part actually is very similar. Last time you use W equals to QV. V equals to W over Q. So it's like work done per unit charge. Q is per unit charge. But that is defining the volt. You may say, oh, miss, I know. Work done per unit charge converting chemical to non-chemical energy or something like that. No. That part is for volt. Define 1 volt and EMF or potential difference and EMF. This one, we're going to talk about just electric potential. So work done per unit charge. Moving a positive charge. Lazy to write positive. You write positive lah, I write a plus sign. Positive charge from infinity to a point. Wow, where does this idea come from? What is infinity? Hang in there. You will learn more where this comes from when you watch the next video after this example about electric potential and electric potential energy. So the main idea here is 2 marks. One is work done per unit charge. You get 1 mark there. Moving a charge from infinity to a point. Wow, what is this? Another mark. Just imagine for now lah. You have a positive charge or negative charge, whatever it is. You have a very far away charge that you're going to bring very close. How much energy is needed? That's one way to talk about electric potential. Okay, so stay tuned. You will learn more about this soon. The second one, state the relationship between V and electric field strength E at a point. How to find? This one, I will pause. We go on first and I'll come back to this. You think about this. How is V related to E? Let's go to the parallel plates. So here you have a beautiful parallel metal plates, 12 or 1.2 cm apart. This is our separation distance. And plate A is earthed. Wow, what is earth? Okay. Plate B is at potential of negative 75. So they already told us one is 0 volt and the other one is 75. Now which one is high potential, which is low potential? How would you draw the electric field? Try and rethink. Last time you learned all these parallel plates one. How would you draw the electric field? Okay, first step. Miss, is straight line right? Yes, it's straight line. So we draw straight lines first. So they should roughly be equal distance. Then where will the electric field point? Up or down? You think slowly. Very carefully. This one is negative 75. This one is 0. Which one is lower? Negative lor. You know, you draw axis. Here is 0. Here is positive 75. Here is negative 75. Which is lower? Negative 75. So this is the low potential plate. This is your high potential plate. Or higher lah, compared to the other one. So when you draw arrows, you should draw it from the high to the low potential plate. So something like this. These are the electric field lines. Okay, so imagine it's like kind of like positive charges here, negative charges here. Kind of. It's a similar system. So what are we supposed to do? Helium nucleus is sitting there. Initially it's at rest on plate A where x equals 0. So this little nucleus start off here actually. Then it will move up until here now. Okay. The helium nucleus is free to move by considering energy changes between the plates. Explain why. So explain is our keyword here. You need to give a reason why. The speed is independent of separation. Wow. So the speed when it reaches plate B is independent of separation. That means eventually this charged particle will reach B. But I don't care how far apart the electric field is, it will always reach at the same final speed. Wow, how to think of this? Okay, we slow down a bit. Let's go back to this plate. What is the thing that causes the charged particle to move? Electric force. Helium is what? Positive. Helium nucleus. Forgot already. Helium 42, chapter 26, also known as alpha particle. So you have positive 2. Okay lah. And if it's positive, it's going to experience a force in this direction, following direction of the electric field. So because of this force, it's going to go up, blah, 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 and go there. But here we're talking about energy, right? So if you want to think about energy changes, first thing you need to remember is work done equals to the charge of that particle times the change in potential that it go across. We already say work done moving a charge. Okay, this one is from infinity to a point. But do you remember this thing? W equals to QV from once upon a time in AS. If you're crossing across a potential difference from high V, wrong highlighter, high V to low V, you're going to have a potential difference. So there is work done, or I would say loss in potential energy, because potential V is linked to potential energy. So this equation kind of represents the loss in potential energy of the particle. Okay, this one is potential related to potential energy. Okay, then what else is changing? Kinetic energy. So you start off with the initial speed, from rest, right? So you start off from U equals to 0. At the end, you have some final speed V. Just write V lah, don't care what is it. Okay, so there is a change in kinetic energy. And is it getting faster or slower? You see the force? The force is pulling it up, right? So it means it is accelerating in this direction. Wow, accelerating means getting faster. So there is a gain in kinetic energy. Also known as, work done is really change energy, right? So KE will be change half m v square minus half m u square. But initial speed is 0, so this whole thing we can ignore lah. So it's just half m v square, final speed. Okay, so we know that conservation of energy, these two have to be related. So whatever you lost equals to whatever you gain. So loss in energy equals to gain in energy. So that will be Q delta V, or this QV. Q delta V equals to half m v squared. Please don't confuse the V. The first V is voltage, potential difference. The second V is velocity. So, oh my goodness. Okay. So this equation is what's going to help us here in the explanation. Why do we not depend on separation distance? You look there. Is there a delta D anywhere in this equation? Look carefully. Open your eyes big. No, right? So you don't care how far apart the plates are. You will still have, it still depends on the potential difference only. The speed depends on the potential difference between the plates. And the charge and the mass. D, I don't care what the D is. So that's what you can explain in your sentence down here. So let's start off by saying, rewriting the equation. QV equals to half mv squared. So because of this, speed or final speed V is independent, means it doesn't depend on independent of separation. In other words, you can say it is not in the equation. So it is, state the obvious, yeah. It is not in the expression. Expression means half mv square, qv. Or you want to say equation, okay the whole thing. Equation means must have the equal sign. Expression is just half mv square. So that is it. 2 marks for this thing. Make sure you remember your basics of electric fields, because these will be useful when you come to curvy radial fields later. Okay, so M1A1. The final thing of this example video is I want to pound in onto the idea of this. So we already look at potential difference, blah, 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 blah. What's the relationship between electric potential and field strength? Now you notice they set up a very nice scenario here. Your helium nucleus start off down here. It rolls to the other plate. Why does it do that? Say, because got electric field. Yeah, but it's affected. The electric field depends on the potential between the plates, right? High V to low V, electric field point this way. So you can think about it this way. I'll give you an analogy. Imagine you go to a playground and you see a slide that looks something like this. You know, where children will sit there and then they're like, slide down the thing, go downhill. Yes, that slide. What is happening there is, let's say one top of the slide is 1 meter high. The bottom of the slide here is 0 meter high. So if you put a particle here, a ball, it's going to roll downhill, right? Why? Because this is sort of called high potential, gravitational potential. High potential to low potential. So it will roll down the slope. But if I change this analogy to electric fields, you can use the same thing. Imagine you are going from a high potential to some low potential down here. So from this point up there, all the way down to the low point. There will be a gradient, a slope. This is what we call the slope. And the nice thing is, if you put a positive charge here, where will a positive charge go? Follow from high V to low V. So it's pointing like that because got electric force. Why got force? Because got electric field. The electric field points from high to low over a certain distance. So I complete the triangle. Here is a certain distance D. So, moral of the story is, this E actually is related by the idea of gradient and slope. Delta V over delta D, also known as the gradient of the potential over a certain distance. So, also there's a negative sign. Why negative sign? Means I roll down the slope instead of roll up the slope. Okay, so just think of this image. You're rolling down slopes from high potential to low potential. And the steepness or the gradient of that slope is what we call electric field strength. Please keep this in your mind when you are doing this question, because you will see this idea keep coming back, but in not so simple situation. It will become more complicated, but if you know this basic idea well, and you can understand it and visualize it, you should be okay. So how do we explain this? I'll just give you a heads up, but you will see this later in the next video. But you can say that the electric field strength is potential gradient. But also, you need to mention that there's a negative sign, like E, the gradient is pointing downwards from high to low, so there's a negative . Okay, so negative potential gradient. But so you can mention that the electric field is in the direction from high to low. And this is our famous equation that we always use. E in AS or previous section, we call E equals to V over D. We always use it, This is where it comes from. But for now, we want to level up. We must include the negative delta V over delta D to show and remind ourselves it's a change in potential over a certain distance. And there'll be a slope, and the slope is the electric field, or negative electric field, which means you're pointing down the slope. Okay, to wrap up the video, here's one final example of how the graph of V and D would look like down here. So this final question is a very recent one, or rather recent one, MJ19 P42. So this is page 29. What is meant by electric potential? Never mind lah. You go and look. You rewind just now. It's the same thing. They always keep asking this definition one, but I'm interested in more in this one. So same again lah. Two plates in a vacuum. One is earth. One is don't know what potential. Positive potential. Point is in the middle. Show the variation of x. Wow, I have to draw graph. Yeah, I have to draw graph. So show the variation of x with potential from one end to the other. So we're looking at how does potential change when you're moving across a distance. By the way, this is 3 marks to draw this graph. Woo! Very nice. So let's go back to the picture. We are starting from where x0 So we say from x0, your particle move, come here to some value x. X equals to x. How does the potential change? Is it getting higher? Is it getting lower? Let's write out the potential. Which one you think is higher? If you look carefully, this is 0 volts. This is plus, I don't know how much, maybe plus 100? I don't know, but some value. So this is definitely going to be the higher V, and this is going to be the lower V plate. Higher potential, lower potential. Electric field line, it'll be something like this, and everything is pointing from high to low. These are all the E fields. So how would you draw potential? Let me give you an example. If the top plate was 100 volts, then here will be 100, right? Positive 100. Then here will be 0. So what is exactly in between? Between 100 and 0, if this is a uniform field, the gradient is constant. So this will be 50 volts here. If I want to cut in the middle here, what is the potential all along this dotted line? 75, halfway through. Here, halfway. What is halfway of 50 and 0? 25, So this is what I mean by the potential is decreasing, but linearly because it's a uniform field. Okay, so once again, reminder of E as delta V over delta D, but remember negative sign. So how are we going to draw this out? You start off where? Here at some high potential, I don't know, V0. Okay, so let's plot that point down in our graph first. When you are at x0, you should be at the highest point right here. Then you travel a certain distance, you go already. You should reach 0 When you travel down to distance x, you should have already reached 0 volts because you have touched the 0 volt plate. So let's put the second point down here. Ding, ding. So what to do now? We connect the dots, That's all we can do. There, something like that. So this is based on the idea that the gradient of the Vx curve is electric field. Is electric field constant all throughout this whole thing? Yes, because it's a uniform field. So write reminders for yourself. This is constant throughout the whole space. Hence, electric field is constant, gradient is constant. So this is the gradient. Gradient, which is dV over dx, or just electric field. Strength, electric field strength. Okay, so this thing is 3 marks by just drawing a straight line. Can you believe it? So the first one is if you draw a straight line. I don't care what straight line, where straight line. If you drew a straight line, you get a mark. Second one is if you have a constant gradient sign. If you're negative, you say negative. If you're positive, you say positive. Okay, and your endpoints are constant. The third one is your final mark if you actually drew the whole graph correctly. So you have a negative gradient. Do we have a negative gradient? Yeah, decreasing. And you must have drawn the line from 0, V0 to the other point, D0. So that is this point up here, this point down there. Okay, 3 marks. So keep this in mind when you go forward, because now we will be moving to radial field lines, not so much of uniform field already. So it's a bit of a level up, but make sure you got these basic ideas in place and you should be good to go. So that's all for this example section. Let's move on to the next part of the theory of electric fields.